Okay. Hello, everyone. This is a laboratory setup for synchronous generator. Uh, we are doing different faults analysis on this. Stator based or rotor based, all faults can be done on this. We have given different tappings of 10%, 20%, 40, 60, 99% for each phase on a stator winding. Machine is placed on the back of the panel. And for rotor faults also, we have some terminals so that we can do some faults analysis on rotor side also. This is a 4 kVA, 4 kVA, 415 volt, three phase star connected synchronous generator. For a supply to the panel, we are taking help of this auto transformer, 12 kVA and 415 volt three phase supply. To connect it with the grid or synchronize with the grid, we have some synchronizing equipment like synchroscope and circuit breakers, MCB. So after running this, after synchronizing it, then we will show you some data analysis. For that, we are using a NI deck analysis. We have one sponsor also like VVDN, if you have seen on. So their company only, they have designed this NI deck. So whatever fault analysis, whatever will happen in real time, I can take all those data through this NI deck, and I've connected for my voltage and current measurements. And all those data I can gather in this and can take in my Excel sheet. And further, I can utilize those data for my algorithm purpose, for my real-time simulations, or any algorithm I want to design based on the analysis. Then I can again put it into my relay system. So these are the two relays, 700G for generator protection relay, and this is for a feeder protection relay. And for three-phase resistive load, this is resistive load of 10 ampere. We have connected. We will see for 1 or 2 ampere also. For current rating, 4.2 ampere of this generator. Now to vary the mechanical input, we have a motor generator set. So we have connected DC shunt motor there only with the generator. I'll show you with diagram also I have. Yeah, this is a generator and motor we have connected to vary the mechanical input. And for that DC shunt motor, we have motor controller here. So from here only I can control the speed, and we'll reach to the frequency of 50 hertz, 400 volt, and when they will match with the grid side, then we will shift to the synchronizing procedure. And after synchronizing, then we can do our analysis and we can draw our data through NI deck and then can do the further analysis. Should I start then? Yes. Okay. It's okay. Hmm. We have a field and armature MCB here. So when I'll switch on those, slowly when I'll increase, it will send the signal to the DC motor, and DC shunt motor is connected to the generator side. Now, if you can see, there is no voltage till yet. Can anyone tell me the reason? Because I am only giving the speed, but not excitation. Excitation is the main heart of the generator. When I'll switch on the excitation system, then voltage will start increasing. So with the speed and increasing the excitation supply, this is 180 volt excitation system. With the help of both of them, I'll maintain a voltage of 400 volt. So this is okay. We have MCB of excitation also. Likewise, when I switch on the field and armature, then I switch on excitation MCB also. Now you can see the little wheel voltage. When I'll increase the excitation, you can see the voltage is increasing, but let's first maintain a frequency to 50. So I'll make it to the 1500 RPM. So let's increase the excitation supply to reach voltage to approximately near to that grid side. To see whether they have matched with each other, what we can do, I can switch on this synchronoscope, and when the synchronoscope will show the very smooth path, then I can switch on. Now it's very fast, so I can't because it's 49.35, it's 390. Hmm. As you can see, from slow to fast, when it come very smoothly, that time I can. So now my generator and the grid side are synchronized. So whatever load I will switch on, both generator and grid will share. And those all things I can analyze in this. This is analytic software. We have a different stacks here. So the first stack is going to the for the current measurement. The second stack is going for the voltage measurement. We have a different total 8 stacks here. So 8 stack I can put differently. Like I have selected voltage here. CDAC mod 8 AI0. Voltage setting I can do 440 and minus 440. So you can see 440 and minimum and maximum I have set minus 440 and plus 440. This is for zoom purpose, also for my analyze purpose, I can do this also. And for recording purpose, I can do this. So it's getting recorded. So after any fault or any analysis, I can withdraw my data. Now, if I'll switch on anything, like for example, current also. There we can select. In place of voltage, I can select current, then current data will. Whatever connection we will do. We have different 8 stacks. Right now I am taking generator voltage. So it will show generator voltage. Now for any fault or any load, for example, if I switch on this load, so you can see 0.6 and 0.4. So 1 ampere load I have switch on. Now for any further analysis for any fault, what I have done, I have taken 2 connections from the rotor terminals. We have 4 rotor terminals here. So I've taken any two out. And for that purpose, what I'll do, I'll switch on any, means those connection I'll switch off. And what will happen, the excitation supply will cut. When excitation supply will cut or any fault will occur in rotor terminals, the terminal voltage will get affected. That we can see in that. But as it is connected with the grid, so that grid will try to maintain that voltage. But for analysis purpose, I know the voltage has dipped, and that I can see in that. Four 40, whatever value minimum or maximum I can put in this. Now when I switch off this, when I'll cut off the excitation supply, then we can observe you can see the dip also, and current has also increased in the stator winding because it starts giving reactive power towards the grid side, and the current in stator winding also increased. Now when I have taken back the excitation supply, still there is a current which is flowing in stator windings. All those process I can do with the switch on load also, 1 ampere, 2 ampere, but I have to maintain that limit also for my generator, which is 4.2, and for rotor side DC shunt motor also it's like 2.4 ampere something. So I have to take care of that current also, so that stator winding or rotor windings didn't get damaged. अगर मैं इसको अभी सिंक्रोनाइज को और बंद करूंगा, then you can see and for any protection also we can send the signal to relay also. Right now I am not connected with the rotor, but if I'll connect for the stator we have connected, if I'll do any fault in that stator, it will show a tripping command also here from relay, and everything is in process. It's in the loop. तो एनआई डेक से हम डाटा भी ले सकते हैं, रिले में भी डंप कर सकते हैं, एल्गोरिथम भी डिजाइन कर सकते हैं. तो आप एक चीज ऑब्जर्व कीजिएगा कि उसकी वोल्टेज भी बढ़ी है. हाँ, किसके लिए? हाँ, एक मिनट, ये सिंक्रोस्कोप के लिए था. उसमें भी जो हमने वोल्टेज कनेक्ट की थी पैरेलली उसमें भी थी. So whatever we have observed in our terminal voltage, wherever I will connect these stacks, NI deck, that data will be shown here, and everything I can collect. Right now I am collecting current also and voltage also. So if I'll choose here voltage, the particular stack, so that data will be stored in recording, and in Excel sheet I can take that out. So in this set we can do stator winding and rotor winding force both. Stator may we have given different tappings, but in rotor we have a limited terminals. But in stator we have a different tappings, 10%, 20%, 40%, 30, 60%, 99% from the neutral end. So I can withdraw the data of neutral end also, current in each phase also and from neutral end also. So after this I can show you that connections also on the. Any questions अगर इसमें भी.
So the data it is collecting in how much sampling rate?
That also we can set as per our own. This software gives every option to us.
Sampling rate meaning in mega. Yeah, in megahertz or like what?
No, for sampling purpose, I'm telling sampling frequency and all those things that also we can set. इसमें.
And also there is one this coupling options, the DC and AC, right?
Hmm.
What if you change like DC to AC or AC to DC?
But here only DC is coming. Up to DC. Maybe in updated software भी हुआ.
तो सब में होता है डीसी और एसी, अभी पता नहीं आपने आई थिंक मोटर सिलेक्ट किया होगा तो ऑटोमेटिक डीसी दिखा रहा हो.
हाँ इस वाले में दिखा रहा है.
I don't know, maybe if we choose AC, so what will be the effect in the data?
कपलिंग का इफेक्ट पड़ेगा बट आई थिंक इन दैट केस अगर लोडिंग हमारा आरएलसी का लगाएंगे उसमें पड़ेगा. राइट नाउ तो हम टोटली रेसिस्टिव लोड ही यूज कर रहे हैं.
वो देखना था, कोई नहीं. मुझे
हमें to just give a basic idea of each panel right now.
पेजिंग तो क्या है,
जनरेटर प्रोटेक्शन ही है.
उसमें क्या करते हो?
मतलब फॉल्ट एनालिसिस ही है. फॉल्ट भी है, स्टेटर एंड रोटर एनालिसिस ही है. तो ओवरव्यू वैसे तो बीटेक लैब भी है मेनली. वी हैव टू गिव a small overview only as per high command order. ये लास्ट वाला जो नॉर्मल तो वो तो नहीं होगा ना.
सब
चलो कोई बात.
Myself, Ashutosh Srivastava. So I'm here a PhD student, fourth year student. So basically, this is the vacuum circuit breaker coordination with the relay experiment. So we are doing this experiment for the BTech students, BTech fourth year students for switchgear and protection system. So the main motive of using that vacuum circuit breaker experiment here is that in other experiments you will see radial feeder, parallel feeder, or distance protection and or CT saturation over OC characteristics. So there are MCBR fuse ELCB characteristics. So what we were doing, we were showing them about the low voltage circuit breaker like fuse, MCB, and contactor. In most of the operation for circuit breaker we are using contactor as a switch separation for switch separation. But here we wanted to also show them that we the main characteristics of the high voltage circuit breaker with the relay means the relay coordination with that. Okay, so the use of vacuum circuit breaker compared to some other high voltage circuit breaker like oil circuit breaker, air circuit breaker, and SO6. All these are depends on the different medium, how we are quenching the arc with the different medium. Okay, so there is some advantage of vacuum circuit breaker like the air, you can say the fast operation compared to other, because the if you see that medium wise, so dielectric strength is more compared to other medium like this. So here we have a 11 kilovolt.
how much time it will be take?
I think the total time is taken is 20,000 cycle. Okay, 20,000 cycle part. The total cycle life cycle time 20,000.
Which time it will be clear? Which time it
Okay, tripping it will depend upon the how much current we have, how much current we have for the different characteristics. So here we are performing for the overcurrent characteristics. Okay, so in overcurrent characteristic we are taking very inverse characteristic and definite minimum time characteristic. So for different characteristic we are showing how much time it is taking. Okay, for different load condition. Okay, twice ज़्यादा चाहिए? अच्छा ठीक है मैं चलता हूँ. Okay, so I will explain what is the circuit diagram, and after that I will do some experiment part. Okay, so in experiment part with different load condition and different overcurrent characteristic I will show. Okay, so here we can see this is the main multifunction meter. So in multifunction meter already we know how much current, voltage, as well the frequency, reactive power and active power we can see. After that we will see about the mechanical part. So in mechanical part we have two type of spring. One is closed spring and another is trip spring. Okay, so one will be charged at a time and another will be discharged at a time. Okay, yes, usually in circuit breaker what is happening. Okay, so a wise will come when I will do the performance of the closed time through automatic or manual. Such as in manual condition, if you see that, we can see that it is in off mode, okay, trim mode. So when I will turn on that, a bias will come, okay, a huge bias will come. So you need to prepare for that bias, okay, such as it is in trim mode, means our circuit breaker is in open condition. So when I will turn on that, okay, so it will change the status. Huh?
Is it safe actually?
Safe. It is safe. Okay, so here the status has been changed, and you have also seen about the charging and discharging of the spring. Okay, so what happened? The closed spring will be charged with the this close button, or here you if you put that, it will be charged. So how it is charged means when you are operating that close coil button, a servo motor is connected with that. Okay, that is charging the spring. Okay, so the trip coil, close coil, and spring charge mechanism I will also explain in when I will do the experiment. Here we are putting the timer. So this timer is not automatically here. We need to put them manually here. So when I will start the operation, parallel simultaneously I will also push that. Okay. So if you see that a three-phase AC supply we are giving to that side, and after that you will see the our circuit breaker is connecting with that. So here relay is connected. What we have done, the relay primary is connected with the line and secondary will be connected to the relay as usual. So we have connected a ammeter. We have connected that ammeter in B phase. Okay. So in B phase we have connected the ammeter. Okay. In series with that line. So we will see the current here also, and we can also see here. Okay. Display of the relay. So this is the CT relay, this is the PT relay. So we are not performing in any over voltage or under voltage. So we will go for only the current part. After that, a three-phase load is connected here. Okay. So a three-phase load is connected here. So basically, this load belongs to a 10 ampere load. 1 ampere 10 load is connected in series. Okay. So this is a 10 ampere load. Okay. 10 ampere load. हेलो हाँ हाँ सेंटर में जैसे पहले लगा था बीचों बीच में हाँ 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 देख लो मैं एक्सपेरिमेंट करा रहा था have two circuitry part, one is the power and another is the control. So control part circuiting has been done. Okay, so we can also understood that part from this figure. So strip coil, closed coil, and spring charge. And if you follow that first figure, VCB and relay auxiliary contact details. Okay, so in this circuit we will see the auxiliary contact part, that is strip coil. 110 volt DC supply will directly go to the off and off. So already it was in off mode. Whenever we will get the supply of 110 volt DC, means here AC supply we are getting through the rectifier, we are converting AC to DC. Okay, then that will be in off position, and when will be on position, from panel to VCB trip coil to VCB trip coil input circuitry will be completed from here. Okay, the same thing will be done for the closed coil when we will give 110 volt DC, and then the spring charge. So here spring charge I have already told that we have connected through the closed coil. But if it will not work through that, then we have also here manual button. Okay, so through manually we need to charge the spring. Okay, through lever we need to charge the spring. Okay, from here. So here earlier condition was this condition is the closed spring. Now we can change here to the circuit breaker turn off. Okay. Next we will go for the relay part. So in relay what we are doing, this is the numeric relay. So the CT ratio is 1 for this relay. Okay. Next is the different characteristic. Okay. This is the very inverse. If time characteristic. Here this is the normal inverse standard characteristics. Okay. Next, this is the plug setting. So plug setting is 20%, and the IN is the rated secondary rated current of the circuit breaker. Sorry, relay. So here it is 5 ampere. This is the time dial setting, which is 0.7. And this is the time for the definite minimum time characteristics. So the time will be fixed. So here it is taken 10 seconds. Okay. We have taken 10 seconds because spring charge will take nearly 5 to 6 seconds. So now it has set a normal inverse 3.0. Okay. So what operation we are doing here? If you see that our flux CT ratio is 1 and flux setting was 0.20 into multiplied with the CT secondary current, which is IR is equal to 5. So our base is 1 and we will see what is the fault current divided by the our primary pickup current. Okay. So here what we will do here, we will just turn on the load 1 ampere. Oh, and after that when we will perform the operation. So it is showing the current value which is 1.221. Okay. So our pickup current value was the 1 and here the current is 1.222 ampere. That's why it has assumed as a fault. Okay. After that operation was performed, this thing is showing that the fault has occurred. Okay. And 17.77 seconds it has taken. This is the time of operation taken by the relay. Okay. So what we are doing next, we are also doing the same thing for the 2 ampere. And through the formula, we are calculating how much time of operation it should take. And the error they are calculating that. Such as, I am just cleaning the fault from here. So for 1 ampere, it is taken 17.77 ampere. The thing is that we have turned on the load which is only 1 ampere, but it was showing 1.23 ampere. So that was coming due to the improper power supply of that. Means we are not getting 415 volt or we are getting something 427 volt. Due to the improper grounding of the supply, we are not getting the balance. That's why it was showing 1.23. So that's why fault has occurred. Otherwise, the pickup current value is the 1 ampere and our fault current here means it is overload condition. We cannot say the fault, but if our overload is too much or we can say it is very rapidly happening. That's why we are considering as a fault to that. So far, if we are doing for 2 ampere, so for 1 ampere, it is 100% increase of that. So we are considering that as a fault.
So how can you measure load in ampere? Load can be in watt, huh?
But here we have connected means correction has been done. So we are considering that resistive load part in
But if you consider that 1 ampere, it should be
like varying resistance we are calculating as a in ampere. So same thing we will do for 2 ampere. So we are showing them for 1 ampere and 2 ampere what happening. Such as it has taken 17.77 seconds for 1 ampere. When we will go for the 2 ampere load, it will take less time compared to the 1 ampere. So now we can see the value of current is 2.172 and now it has taken 5.912 seconds. And one more thing, the total time is nearly 5 seconds. Okay. So that's why further it will take less time. That's why we are not doing more than 2 ampere. Okay. Here. The thing we will do, we are doing here with the change characteristics. We are also doing for the very inverse. So if we follow the different characteristics of inverse time over current relay, then we follow that initially our very inverse was taking more time compared to the standard inverse. But after a critical point, you will see that very inverse will take less inverse. Extremely inverse will take more less time, very inverse take more less time. So other thing we will do the same. Here again we will do for the 1 ampere. Okay. हाँ बस 2 मिनट. So earlier for standard inverse, it was taking nearly 17 seconds. So let's see how much time it will take. The same thing we are doing for 2 ampere. So it has taken 29.19, maybe due to the low value of load fault current. When we will go for the 5, 6 ampere or maybe 10 ampere more than that, then maybe the characteristic will be different. One more thing we will do here, we can do for the definite minimum time. So if we will do the definite minimum time, so let's see how much time it will take. So as we have said already, the definite minimum time, which is 10 seconds. So it has taken 10.22 seconds. So that 0.22 second is the human error, what we have done. Okay. So some other things also we are doing in the experiments, means self-clearing fault also. And when we are doing for 1 ampere, then suddenly we will increase the current. Okay, for 2 ampere or 3 ampere we will do. So how the time of operation will time with that operation we are showing. Okay, so many different things are there, but we have less time. That's why I have shown only 3 characteristics to this. Okay, any question you can ask? आपका कोई भी डाउट है बताइए. Okay.
It is strange, right? Maybe itself is not using their relay in their own panel.
Then what we are using? Means this is the interactive session. You have any inputs you can give. Please, you are already now. And one more thing, such as you are in industry where then means it is means a huge sound is coming. So it is also in air blast.
Particular setup is for transformer protection. To make complete substation, one of the important aspect is the transformer, and how we can connect the transfer protection devices in a smart substation. So the idea is, first, these two are customized transformer. So we have a 3-phase transformer as well as a 3 single-phase transformer connected in a 3-phase bank. And each transformer you can access the terminals, different winding locations, and single turn, 5 turn, 10 turns also. So you can check whether what will happen if we have the 10 turn is short or 5 turn is short or single turn is short. What will be the impact on the currents? You can check your algorithms, whatever things you need to, all the scenarios of internal fault, external fault. So in this transformer, this setup, we have recorded a inrush peak of 75 amperes and fault current of around 20 amps. So for this transformer rating of 5 kVA, the current rating is 7 ampere, and almost 3 times we have created a fault for this setup, and we checked our algorithms. Now, how the circuit is connected? We generally if you see the C over here, C is nothing but a circuit breaker. So we can connect this on that circuit breaker terminals, we can get it back over here. Then it is connected to the primary of the CTs. Then the secondary of the secondary is left open. There are 2 connections you can do. The first one is you can connect to this existing in-service relay, and the second one is you can create your own algorithm and connect to your relay. Then you can connect to transformer. Again, secondary will be having the CTs, and it will go into the loop. Now, whatever the CTs are there, CTs can be connected to this sensing kit. So what does this kit do? When you create a relay, you cannot connect a power signal directly to the relay. There will be some conversion required which can convert the power signal into a control signal. Let's say if you have a 1000 ampere rating, you cannot give 1000 ampere or directly to the relay, right? You will be required current transformers. You connect a current transformer over there, it will be converted to secondary. The secondary, let's say, is 1 ampere. Now that again 1 ampere you connect to the relay. This relay can connect on 1 ampere. But if you have a DSP, you cannot connect to 1 ampere. You need to convert that into approximate voltage levels. So what we have done, we have using a DSP controller based on TI, and we are creating our protection algorithms. TI has the limit of 0 to 3 volts only. So you cannot give negative, you cannot give above 3 volts. So these circuits convert the whatever the current we give it to him, and it convert to the 0 to 3 voltage limits. Now this 0 to 3 volts will be given to the ADCs of the Texas Instrument board. So you connect on the ADCs, you configure the ADCs, then there is a CPU over here. You dump your protection algorithm on the CPU. It will take a decision whether the condition is normal operation, faulty condition, abnormal operation, whatever the condition you simulate on this panel, you can get it. Then it will provide you the tripping logic. The tripping logic is nothing but the change of GPIO. When you change the GPIO, again, you cannot connect this to this circuit breaker. You need to have some interfacing circuits. So we use an auxiliary relay which can carry the circuit breaker trip coil current. So normally it is in an open state. As soon as this circuit gives the trip command or a one signal from GPIO, it will convert the auxiliary, it change the status of the auxiliary relay, and it make the trip coil of a circuit breaker. As soon as you make the trip coil of the circuit breaker will be tripped, and this portion will be removed. So the complete operation for one protection cycle you can perform. You can check what is the response time of the relay. You can check what is the response time of the circuit breaker, and you can also check what will be the response time or fault clearing time from inception of fault to the clearing of the fault. Now, to get these things, what automation we can do? So if you know, currently the automated substation are replaced by merging units. These merging units will sense the cookies. At the field level only, it can convert to the digital signals or sample value packets. You will see how the packets and everything will work tomorrow. But this sample value packets will be directly connected to the relay. So this relay will have a LAN connections. Multiple buses will be there. You can connect to the Ethernet switch and it will go to the relay. Instead of sensing current, now it will get a digital signal from the Ethernet. And then it will send you, algorithm will be same, and the decision will be transferred to the circuit breaker using a goose protocol. So that automation you will discuss tomorrow, that how goose and everything will be interfaced with this type of relay, SEL relays. Right? If you have any question, you can ask. So whatever the protection logic you have, you can make in any DSP. And same thing, what if this relay configure or whatever the performance this relay do, same thing it can done by this. Everything.
Also save the data.
We can save. So data saving is very simple. Logger is there. You can connect a logger over here. DSO is there. If you don't want to connect DSO, you can use current clamps. Simply connect a clamp over here, it will record. And DSP also somewhat say based on the RAM proportion. So which DSP you select for the application, it will depend on that. એટલે આ અમે લોકોએ છે ને ડિઝાઇન કરીને બનાવડાવી છે બહારથી પરચેસ કરો હા ડિઝાઇન કરી બટ સેમ થિંગ યુ કેન મેક so this is generalized kit. So this you can use for TI, this you can for STM, this you can use for FPGA as well. So આની પર બધા પોટેન્શિયલ નોબ છે. તમારા વોલ્ટેજ રિક્વાયરમેન્ટ ના પ્રમાણે તમે પોટેન્શિયલ નોબ ને ચેન્જ કરીને તમે ચેન્જ કરી શકો છો. ના 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 આઇસોલેશન સ્કેલિંગ માટે એન્ડ કન્વર્ઝન. સો સિટી કરંટ આપશે તમને બટ તમે કરંટ ના આપી શકો ડીએસપી ને. ડીએસપી વોલ્ટેજ માં વર્ક કરે. તો તમને હું કહું 1 એમ્પિયર, તો 1 એમ્પિયર ને મારે વોલ્ટેજમાં કન્વર્ટ કેવી રીતે કરવાનું? અને એમાં એવું ના થાય કે 1 એમ્પિયર ના કશું રેजिस्टर લગાવી દઉં અને એને કન્વર્ટ, એવી રીતે ના થાય આમાં. કારણ કે જો 1 એમ્પિયર અગર રેजिस्टर લગાવો તો તમારું બર્ડન વધ્યું, સિટીનું બર્ડન વધાર્યું ને તમે. એટલે આ એલિયમ છે, હોલ ઇફેક્ટ સેન્સર છે. એટલે હોલ
આપણે જે ડીસી છે એમાંથી 12 વોલ્ટ જે રિલે ને આપવા હોય તે સ્કેલિંગ કરીને રિલે ને એડિટ આપશે.
સો આ કેવી રીતે આપે છે? સિટીની સેકન્ડરી કોઈ દિવસ ઓપન સર્કિટ ના હોય, શોર્ટ સર્કિટ જ હોય. બટ એ શોર્ટ સર્કિટ પર જ્યારે હું શોર્ટ સર્કિટ કરું ને એમાં મેં હોલ ઇફેક્ટ સેન્સર્સ લગાવ્યા. હોલ ઇફેક્ટ નો ફિનોમિનન શું કે જ્યારે કરંટ કેરિંગ કંડક્ટર જ્યારે પાસ થાય તો એ વોલ્ટેજ જનરેટ કરે પરપેન્ડિક્યુલર ટુ ડિસ્ક. એ રેગ્યુલેટર આઈસી ને જાય છે, એ વોલ્ટેજ યુઝ છે. એટલે તમારા સીટ આપણે એવું કહીએ કે ઇલેક્ટ્રો જો ડિજિટલ રિલે નું બર્ડન બહુ જ ઓછું હોય છે. કેમ ઓછું હોય છે? અદરવાઇઝ હમણાં મિકેનિકલ રિલે તો શું 1 એમ્પિયર ને હું કોઇલ ને આપતો, એટલે કોઇલ ના લીધે મારું બર્ડન વધે. આમાં તમે કોઇલ ને આપતા નહીં, તમે ડાયરેક્ટ શોર્ટ કરો છો અને એની મેગ્નેટિક પ્રોપર્ટીઝ થી તમે સેન્સિંગ કરો છો. એટલા માટે ડિજિટલ રિલે નું બર્ડન સૌથી ઓછું હોય. અદરવાઇઝ મિકેનિકલ રિલે તો તમે કોઇલ ને આપો, એ કોઇલ જે રીતે પરફોર્મ કરે એ રીતે તમારું ડિસ્ક ફરશે. પણ આમાં તમે કોઇલ જ નથી, સીધી સેકન્ડરી છે. એના જે વાયરમાંથી જે મેગ્નેટિક ફિલ્ડ પ્રોડ્યુસ થાય છે એના બેઝ પર તમે હોલ ઇફેક્ટ સેન્સર લગાડીને તમે સેન્સિસ કરો છો. એટલે તમારું ડિજિટલ રિલેનું બર્ડન સૌથી ઓછામાં ઓછું હોય. એટલે આ જનરલાઇઝ છે, તમે આને કસ્ટમાઇઝ કે નાની કરો તો તમારા રિલે અંદર ફિટ થઈ જાય. આમાં વોલ્ટેજ કરંટ બધું સેન્સ થાય છે. જનરલી 787 87 ખબર તમને 787 કેમ નામ આપે છે?
હા
87 એનો પ્રોટેક્શન નંબર ડિફરન્શિયલ 7 ની ઇનપુટ. So no, so transformer, so 3 phase, 3 primary, 3 secondary. 471 is V by F. So transformer now you need to protect transformer from overfluxing. So V by F. So voltages you can sense. Otherwise, in differential there is no read of voltages. Because cost of PT is we cannot afford. But to check overfluxing, we need optional V by F protection. Overfluxing protection. That is why 787 itself.
Used in OpenID, right?
This is OpenID port. OpenID का port है. We have OpenID as well. We have 3 OpenIDs.
OpenID is the subject.
2 OpenID. But we have a BMS with OpenID, Battery Management System, which is one of the kind. You can check the BMS algorithm to design on a EV simulator. Right to OpenID. Different level.
कोई दिखा सकते
Tomorrow we'll see. We have the multiple sessions, na? So tomorrow you will see different labs. So for today, only this lab is there.
So, I think you have discussed about the generator protection.
Yes.
So normally in power transmission system or in a general power system, in generator power is generating, then you have gone across the transformer. Transformer will step up, and then through transmission line the data will flow to the another substation. There we will step down, and then it will go to the loads. Okay. So here we will discuss about the transmission lines and how to protect the transmission lines. So there basically we use distance protection in this case. So in the distance protection, as you may know, we generally use 3-zone protection. Okay, 3-zone protection means, do you know? Shall I explain? Shall I explain? 3-zone protection. You know, right? So I will give an overview. Like there is a transmission line. It has a certain impedance. So in the 3-zone protection, for the first zone, which is known as the primary zone, and if an fault occurs, normally we keep it as 80% of the line. So let's say we have a 100 ohm line, 80%, 80 ohm, we will keep that as a first zone. And if any fault occurring in the 80% of the line, it falls under the first zone. And normally with the time setting which we will give, it is usually instantaneous. So first zone If it is falling, instantaneously we will trip. Then in the second zone we usually keep between 80% to 140, 150%. Okay. So if it falls in this range, then we will trip after certain delay. We will not trip instantaneously, we will trip after certain delay. Okay, delta T. Okay. And in the third zone, it will be another some delay. So delta T1, if we add there it will delta T2. So it usually from 150 to 200 or 220% we will keep. So basically, why we are making this 3-zone protection? To give backup. Okay. If one relay falls, let's say we have R1, which is protecting first line, and R2 is protecting second line. And in the second line, at 40%, fault has happened. Okay. So in normal case, R2 should detect because it is falling under its first zone. So R2 should trip instantaneously. But if due to some mal-operation or due to misoperation, it fails to operate R2, then that 40% of fault from R1, it is 140%. So it comes under second zone. So it will trip, it will wait for R2 to trip. So that delay which we gave, that is we are waiting for R2 to trip. If it is still not tripping, after delta T1 time, R1 will trip and it will isolate the problem. And similarly like this. So the relay which we use normally in distance protection is Mo relay. Okay. So in the UG course, this panel we have developed. So this panel says that there is a grid, there is a motor generator set. Okay. So initially we designed like this, like there will be a gate, there will be a motor generator set, and we will synchronize them, both of them. Okay. So we have synchro scope and we will synchronize them. But currently we don't have motor generator set here. So directly at the end of this bus, we have given it to a 3-phase load. The power is coming from the grid and flowing through this transmission line to the load. Okay. So now this is the transmission line. So through this 3-phase variac, we are giving 3-phase power. Okay. So through this variac, we are giving 3-phase power and we are giving to the starting of the bus. Okay. And then we have this transmission line. Actually, it is written here bus 1, bus 2, bus 3, but actually there is only one line, bus 1 to bus 3. Okay. And we have divided the line into multiple pi sections. So you know pi sections in the median transmission line, we usually use two types of models, T model and pi model. And usually pi model has advantages over T model. Why? Because in pi model, we have less number of nodes. In pi model, we have only 2 nodes, input and output. We have 2 capacitors and 1 RL in series. But in T model, we have a node in the middle. So as you know, as the number of node increases, if you do load flow studies and other studies, as the node increases, the computation capability should be more. It takes more time to converge. Okay. So that's why we generally prefer pi section models. So here we have this pi section. Any doubt until here? So this is a pi section model, different models. And then at the start of the bus, 3-phase power is coming from here, 3-phase RYB, and here we have kept CTs. So we have kept it at the back. So we have 3 CTs for 3 phases. Okay. And then this is the primary points of the CT. So this line we have given it to the primary, and the secondary of the CT is connected to this device. It is actually called CL351 protection system. We can use it as a PMU. We can use it as a relay also. Okay. So secondary of CT, we have given it to this relay. Okay. Similarly, this bus data, this bus 3-phase voltages, we have given it to a PT, and the secondary of the PT, we have given it to the relay. And this relay is connected to this system through LAN wire. So basically in this, for this course, we are focusing how the data is being transferred and there how we are monitoring it. So there only main focus will be there. Okay. So now this is the complete line, and here as there is no motor generator set. So we have given CT connections for that, but as there is no motor generator set, we have shorted this to complete the path. Okay. And at the end of this load, end of this bus, we have connected this load. So this is the 3-phase RLC load. Okay. So this is the 3-phase RLC load. So this is actually the panel. And now in the UG experiments, what they do, they create faults at different locations, and 25%, 50%, and they draw more characteristics, 3-zone characteristics, and in which zone it is falling, they just mark it. So in UG, they do like that. So for that, let's say we are creating a R phase fault. So through this switch, this is the fault resistance, and the end of the fault resistance is connected to the ground. So like this, we are creating R phase fault, R to G, LG fault we are creating. Okay. So let's give around some 100 volts, something like that here, 100 or 110. So this is showing line to line voltage, RY phase line to line, and this is showing only phase current, R phase current. So now let us come to this computer. Okay. So So this is the software of accelerator quickset of that SCL relay. Okay. Now I am calling it as a relay. It can work as a PMU also. So in this only we will choose whether that relay should operate as a overcurrent relay or it should work as a distance relay. So if it is working as a distance relay, we will give the impedance 3-zone settings. So zone 1, it's what impedance should be there. Zone 2, what impedance should be there. Zone 3. So that settings we will give here. Here we are not tripping anything. For tripping, how the relay, as Professor Sidhu has told that for relay we use goose communication nowadays. So how that goose communication looks like, how we are tripping it, tripping the circuit breaker, that we will discuss in tomorrow's session, where I will show you the relay to circuit breaker goose communication. Okay. Here just we are monitoring what data is flowing. Okay. So here, if you go to this HMI, so here I have given the line settings over here. Okay. So anyway, it is not required because we are not tripping anything. So if you click on this HMI, so this is the main panel. If any relay is tripped, it will show trip, all the status. So all these things we will discuss tomorrow. But main thing is, if you click this instantaneous values, so here we are seeing 3-phase voltages, 3-phase current, their magnitude, their angle, and we can see real power, reactive power, power factor, all these things we can see here. Okay. So as you can see, so this is showing 0.0262 kilovolt. So 62 volt, that is line to line voltage. So this is phase voltage. So there is imbalance from the grid. So as you can see, this is 62, 64, 64. So there is some imbalance from the grid. And current is same, the 0.109 or something like that it is showing. Now we can create fault at different locations. So we are creating this R phase fault. So at 25%. So if we create the fault, you can see the R phase current has increased from 0.109 to it is showing something 1.084. Okay. So we can note down this reading. We can collect this data every 1 second. It is refreshing. Okay. So we can collect this data in a ComTrade file or in a CSV file also. Okay. So all these things we can do here. And the UG students, they collect the data at different fault locations. So at 50% if you do, so again same thing they will do. They will note down the readings and they will. So the UG students do that, but main focus hour is how data is being transferred, and the same software being used in the other panels also. All these panels, this feeder protection relays you see na, here also there is a feeder protection relay. Same software we use to do the settings, and that relay can communicate to this software and we can see the data also here. Okay, so like this, the data is being transferred from the relay to a software or to a PC remotely placed. Okay, so this is how it works. Okay, so this is about it.
Basically, laboratory, what we have designed is that protection or maybe substation perspective protection if we design or we study. So generator you have already done, then transmission line is there. Then from distribution perspective, we have a different configuration of feeders, say it feeder radial feeder configuration, and then we have parallel feeder configuration or ring main configuration. So these are the panels which are designed to first analyze their protection perspective, like how we design protection scheme, then role of these digital relays or IEDs, how they sense fault, how primary and backup protection. So what we'll do is first I'll explain the panel connection like what we have done. Then we'll eventually discuss its practical significance and their working. Okay. So first I'll explain the just basic hardware का मैं दे देती हूँ. Then he'll explain the complete. Okay. So consider it so that you can understand what we are doing basically here. Okay. So here supply. Consider it as a supply source to load. Load is like consumer and consider us. Okay. So this is our 230-volt supply. Then CT is connected here. Primary and with CT secondary, our measurement or sensing devices are connected. So this is our relay. Then this is one feeder of 6.5 ohm. Then another feeder, same configuration CT. CT के secondary से it is connected relay. Then we have designed a load side, maybe consumer side. Okay. So here the protection scheme will be unidirectional. Current is unidirectional in radial. So protection scheme basically in distribution side what we use is overcurrent protection. So protection criteria will be only current sensing. So plug setting and TDS or whatever protection scheme we will design and he'll demonstrate, that would be based on the current setting. Direction ka there is no rule, no role here. Okay. So he'll explain the principle.
So as you can see, ma'am has told all about the basic things. So here we have a load, that's consumer end only. If we, let's say if we create a fault over here, that means we have set up over here a MCB. That means MCB should trip first. So let's take create a fault over here. Instantly MCB has tripped. That's a function of MCB. Then if let's say if we have a relay R2, we have a relay R1. Let's say MCB doesn't trip. If it's maloperated, something is happened. That means relay R2 should provide a backup protection for this. And if let's say relay R2 doesn't work, then we have a relay R1 that will work after this. Okay? Then for this we have a from MCB to relay R2 we have a coordination time interval we have provided, and we have all the setups in this plus setting, time plus setting. We have we can see it from here. Right? You can go to this. No, we have connected this relay. Yeah, we are not connecting this one. This R2, this R2. Both are same. With this both are same. We have just connected this first. Then after that we can see this also working. So from here we can see the values. Maximum phase PUC. We have 0.5 ampere set PUC. We have time dial setting. We have a 0.6. We have for this configuration. We can for this also 0.95 time dial setting and TOC 0.7. So let's create a fault in this. If we create a fault for this, that means relay R2 should operate first. If we create a fault,
Actually, वो रहेगा. Okay, so basically, meanwhile he changes the connection. I'll explain. See, there you can observe two relays. One is the older generation electromechanical relays, and this is the new generation IEDs or digital relays. So these are obviously these are the most advantageous relay. Like with previous batch we just discussed that these electromechanical relays fine. These are robust and local for local control and local operation. These are very good. But what and another basic advantage is that they were not communication capable. So cyber attack issue minimized over here. But what are the disadvantages? Like first, these are not communication capable. That means that whenever local control or maybe locally we cannot operate, we have to always operate them manually. And secondly, these digital relays, for example, these are following IDMT characters. So if we use maybe different characteristics, maybe for our application we need inverse minimum time characteristics or very inverse characteristics, then we have to use whole together a different relay. But here in these newer generation relays, we can just directly feed in our characteristics. Even we can write our own custom characteristics. Secondly, these are communication capable. So within relay communication, maybe we discussed in our lectures also, who's communication capable. And also continuously they records all the events, all the data, all these things, and directly we can communicate with SCAD. You might have observed that for substation automation or distribution automation, the highly useful very make everything convenient. This is what feeder automation looks control also is very easier with these.
so as you have seen, we have created a fault here, then relay should R2 should operate. If we same goes for this, if we create a fault in this, then our relay R1 should operate. If relay R1 has operated, then after this, if we need to see whether if let's say relay R2 is operating, but it doesn't operate, there is a maloperation is there. That means for backup relay R1 should operate. For that we are bypassing this. We are using this commutator to bypass. Then we for this we have a connection for this. So let's demonstrate that also.
Protection scheme is designed with but that whichever protection device is there, firstly, foremost, that should have instantaneously protect that area and it's healthy and quality section should be stability. But what if that protection scheme doesn't work in the given time? Then the backup protection scheme is. And when and how the backup come into picture, what we protection coordination is what it is. For example, coordination timing for time grid. So this is what he'll demonstrate.
So as we create a fault in this, that means relay R2 will give us signals of breaker failure. Then after that, relay R1 will operate. Let's create a fault. See, he's given a relay break. Then here break has been elected. So this is the functioning of this. We can go to parallel.
What occurred then only that should be isolated. Healthy section remain
Same.
the same so that continuity of power supply can be maintained. So we have to design these relay and have to grade them such that or all four within operating standard sustainably perfect. Second thing, whenever fault current, see first fault current would come when fault occurs in this figure. But the same fault current would go into but also come in from that direction also. So these where the section would get 40. So the plug setting and TVs and time rating we design it in such a way that if what occurs in this window, then only these should act, this shouldn't do what occurs in this feeder and this should act, this shouldn't. And what if in case of failure scenario? Maybe failure of circuit breaker. That design in such a way is fails to operate for a case fault in circuit with R1 should be at its value. Like protection immediately. And similar for R1 management. Or a radial feeder or windmill configuration. There can be different possibilities. Clear? Time for so then there are some rules to that. Observe it also by observation. So rewrite when I'll explain that what have learned consistency is this. The these are container even those sensing device. What it does in the point of view. You know, we do not expect such a many open contact. So in this way isolates the heavier bodies. So this C1, C2, जब हम बैठ वो अपने यूट्यूब कंटेंट को kind of different color. These are the directions. Either flip direction. Correct.
Let us say 180-degree phase shift.
You can observe all these readings whenever it flips. All the zones are compensating. और फिर उसने जो फॉल्ट करंट सेंस किया है वो जो करंट ट्रेवल करके आया so that would obviously is lower in value. That is why it acted first and then it acted. Okay. And for the time of operating, we can directly observe the right? Time stamp will over that. You can directly observe.
Sir, parallel feeder, sir. तो दोनों साइड से करंट जा रहा है, तो जहां पर फॉल्ट हो रहा है वापस घूम के वापस आ रहा है। लेट्स से फॉल्ट इधर, तो करंट ऐसे घुमा, देन वापस यहाँ पर।
Current is very high initially, so it acted first, and then current travel back later. We have designed their protection in such a way for we have simulated with such a way that we have bypassed the one. So it says, but then would be unable to open the contact for sale of 30
This will not.
and then this should also go along the first when we have to try to open the contact but can't do. And then they can
But this period was changed and why that full current led to this as well.
current form.
Sir, they have get it.
So उसको पाथ तो कंप्लीट करना पड़ेगा ना।
Fault feed करेगा both
I
parts.
was sorry that fault was that's actually.
Very well. Fault like
No, I work and work the
okay.
Yes.
So main idea behind is that sign of the protection scheme and secondly use of the so coming these are some of the general open sir maybe we got it. Events are continuous law of all the residents. And these are the dimensional events from the order of. These data are also current in the intelligence.
So also communicate with the people.
It's not I
PM can also fetch that.
if it's not required actually. If the automation purpose failure, substation automation purpose will be IPT automation.